Full fine-tuning runs out of memory fast. TRL, PEFT, bits and bytes, and QLoRA will produce a 4-bit adapter on one GPU without updating the frozen base model. You'll learn how the pieces fit into a workflow that tunes examples and saves a compact adapter while leaving the original model unchanged. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Large language models are hugely capable, but they're also huge. If you try to update every weight, you quickly hit memory limits. QLoRA with PEFT and bits and bytes gives you another route. Keep the big model frozen, quantize it to 4 bits so it fits, and train only a tiny adapter. The result is a compact artifact that captures task-specific knowledge without needing a cluster of GPUs. Think of the base model as a library. QLoRA compresses the shelves so they fit in a small room. PEFT adds a sticky note system that changes behavior without altering the books. TRL is the trainer that applies those sticky notes during supervised runs. Together, they let you iterate cheaply and fast. We will build a tiny supervised fine-tuning example that produces a saved adapter and a quick eval score. That keeps the demo focused and makes the memory behavior easy to see before we scale up. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we create and inspect a tiny dataset while the GPU is still untouched. This snippet creates a tiny supervised fine-tuning dataset using Hugging Face datasets. Before we touch GPU memory, it's important the data shape is predictable and easy to inspect. Each row has a single text field with a compact instruction and response, which is the default TRL format for simple SFT runs. Dataset.fromList keeps the examples in CPU memory, and train-test-split gives us deterministic train-ds and eval-ds with seed equals 7. The printed row counts confirm we have both training and held-out data before the model ever loads. With data ready, we load the base model in 4-bit so it fits a single GPU. This example loads the frozen base model in 4-bit form with transformers and bits and bytes. The memory bottleneck shows up when you load the model, so bits and bytes config is the first real QLoRA step. Load in 4-bit. True swaps supported linear weights into 4-bit quantized layers, while BNB 4-bit quantype equals NF4 matches the common QLoRA setup. AutoTokenizer prepares the matching tokenizer, and the pad token fallback avoids batching surprises in TRL later. The printed quantized GIBI value tells you the model footprint after quantization, a key checkpoint before adding trainable adapters. Next, we prepare the quantized model for adapter training, so only a few parameters will learn. This code prepares the quantized model for adapter training and attaches a PEFT LoRA configuration. Instead of updating the base weights, QLoRA keeps the model frozen and trains small adapter matrices. Prepare model for K-bit training applies the PEFT K-bit preparation. Then, LoRA config defines the adapter rank, scaling, dropout, task type, and which projection modules to target. Get PEFT model wraps the existing model with those trainable LoRA layers. The printed trainable PCT shows how little of the model will be updated. That's why this fits on a single GPU. Now, we run a short supervised loop with TRL to adjust those adapters and verify training works. This snippet runs the actual supervised fine-tuning loop with TRL SFT trainer. The adapter is already attached, so the trainer gets the PEFT wrapped model, train-ds, eval-ds, and tokenizer through processing class. SFT config keeps the run intentionally small, with max steps equals 10, while gradient accumulation steps equals 4 lets a batch size of 1 act like a larger effective batch, without blowing activation memory. A higher learning rate is typical for LoRa-style updates because far fewer parameters are being trained. The printed train loss gives a quick signal that training ran and produced a measurable result. Finally, we evaluate and save the compact adapter so the experiment is reproducible and reusable. This example turns the short training run into a reusable adapter artifact. Engineers comparing experiments want a numeric eval and a saved directory they can reload later. Trainer.evaluate returns the held-out loss from the TRL trainer, and math.exp converts that loss into a simple perplexity-style score for quick comparisons. Trainer.model.savePretrained writes the PEFT adapter weights, while Tokenizer.savePretrained keeps tokenizer assets alongside. The printed adapter path and eval PPL show both the exported artifact and the evaluation signal for tracking the run. In a realistic pipeline, you'd swap the tiny dataset for your domain examples and run a longer schedule. The same saved adapter directory can be merged at inference time or loaded alongside the frozen base model for fast deployment. This pattern keeps experiments reproducible and model storage compact. What we built is an adapter-based QLoRA fine-tune, a tiny number of parameters trained on a quantized base. Use this when you need task adaptation on a single GPU, without changing the original model. One caveat: adapters have limited capacity, so very large or complex tasks may require a higher LoRa config rank or more data. A practical next step is to raise the LoRa config rank R and rerun training on a larger domain dataset, such as your support logs. Then compare eval PPL between runs to find the smallest R that gives acceptable quality. That change directly trades memory and training time for adapter expressiveness. If practical AI engineering helps, subscribe and watch the AI engineering videos.